There is a belief you carry quietly, that you understand what dense means. You hold a brick, you feel its weight, you imagine that, scaled up, is what a collapsed star must feel like. You are wrong. Catastrophically, beautifully wrong. A single sugar cube of neutron star matter weighs more than every human on Earth combined. And tonight, you are going to fall into one, not metaphorically. We will take your body, release it from a safe distance, and follow it second by second as physics rewrites everything you are. If this calms your curious mind, gently tap like and subscribe so we can keep these journeys going. Before we begin, whisper where you are watching from and what hour reaches you tonight. There is something you already know about stars. You learnt it as a child, probably looking up at a clear night sky from a backyard or a window or a car parked somewhere far from city lights. You learned that stars are hot. You learned that stars are bright. You learned that stars are very, very far away. And all of that is true. Every word of it is true. Astronomers have spent centuries confirming exactly that. The sun, sitting at the center of our solar system, burns at a surface temperature of nearly 6,000 degrees Celsius. The light reaching your eyes from the nearest star outside our own took just over 4 years to arrive. The light from the more distant ones has been traveling for thousands of years. Some of the stars you see tonight are no longer there. They burned out long before you were born, and their final light is only now catching up with you. So yes, stars are hot, stars are bright, stars are far away. This is the comfortable knowledge most people carry, and for most stars, in most cases, that knowledge is enough. A star is born inside a cloud of gas. It lives for millions or billions of years. It burns through its fuel, and then, when the fuel runs out, it dies. Some stars die quietly, fading into a slow, cooling ember that drifts through the galaxy for trillions of years. Some stars puff their outer layers off in a soft, expanding shell and leave behind a small white core. These are gentle deaths, predictable deaths, deaths that obey the rules. But some stars do not die quietly. Some stars do not fade. Some stars do not drift. Some stars die in a way so violent, so absolute, so contrary to everything your intuition tells you about how the universe should behave, that the matter they leave behind stops being matter in the way you understand the word. The atoms break. The protons and electrons that built every familiar thing in your life, the iron in your blood, the carbon in your skin, the calcium in your teeth, those building blocks are crushed together until they cease to exist as separate things. What remains is a single object, so dense, so impossibly compact, that a piece of it, the size of a sugar cube, would weigh more than every human being currently alive on Earth combined, stacked together. Every body, every bone, every breath, all of it, in a cube small enough to hold between your finger and your thumb. That object is called a neutron star, and before this video ends, you are going to fall into one. But first, you need to understand what it took to make it. Because the birth of a neutron star is not a quiet event. It is the most violent process the universe knows how to perform that does not involve a black hole. It begins, like every star, with a balance. A star is essentially a controlled explosion held together by its own weight. Inside the core, hydrogen atoms are being crushed together by gravity at temperatures hot enough to fuse them into helium. That fusion releases enormous amounts of energy, energy that pushes outward, energy that wants to blow the star apart. And at the same time, the star is pulling inward on itself. Its own enormous mass is trying to collapse it. For most of a star's life, those two forces are in perfect equilibrium. The push outward from fusion is exactly equal to the pull inward from gravity. The star is a billion-year-long argument that nobody wins, until the fuel runs out, When a massive star, a star at least 8 times the mass of our Sun, finally burns through its hydrogen, it does not simply stop. It moves on to fuse heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon. Each new fuel burns hotter and faster than the one before it. Each new stage of fusion lasts a shorter amount of time. Hydrogen burning might last 10 million years. Helium burning, 1,000,000 years. Carbon burning, perhaps a few hundred. By the time the star reaches silicon, the fuel that comes just before the final stage, it has only a single day left to live. One day, after 10 million years of burning, the last layer of fuel will be exhausted in 24 hours. And then it reaches iron. Iron is the wall. Iron is the element that fusion cannot push past. Every stage of fusion before iron releases energy. Iron fusion absorbs energy. The moment the core of a massive star becomes iron, the outward push that has held the star together for its entire existence simply turns off. There is nothing to fight gravity anymore. Nothing. And in that instant, an instant that lasts roughly a quarter of a second, the core of the star, an iron ball the size of the Earth, collapses inward at nearly a quarter the speed of light. A quarter of a second. That is how long it takes. A star that has been alive for tens of millions of years is undone in the time it takes you to blink. The collapse is so sudden, so violent, that the iron core slams into itself and rebounds. A shock wave of unimaginable energy tears outward through the rest of the star, blowing the outer layers off into space at speeds that can reach 10% of the speed of light. For a few weeks, the dying star outshines its entire galaxy. Astronomers on planets billions of light years away can see the flash. This is the supernova. This is the death cry. This is the moment that scatters newly forged elements across the universe, the moment that seeds future planets with the heavy atoms that will one day become rivers and forests, and the iron in your own blood. But the supernova is not the end of the story. The supernova is only what happens to the outside. Inside, at the very center, where the iron core has crushed in on itself, something stranger is taking place. The pressure at that center is so extreme that the electrons inside every iron atom are forced into the protons. Electrons and protons combine to form neutrons. The familiar structure of matter dissolves. There are no atoms anymore. No nuclei separated by empty space. No electron clouds. Just neutrons. Trillions upon trillions of neutrons, packed so tightly that they touch. A solid ball of neutrons. A neutron star. Now, before we go any further, I want you to do something simple. I want you to picture a city. Not a metaphorical city, an actual city. Pick one you know, maybe the one you live in, maybe one you have visited. Picture its skyline. Picture the streets you have walked. Picture the size of it from edge to edge. If you live in a smaller town, picture somewhere larger you have seen. Manhattan, Paris, Tokyo. A city you can hold in your mind. A place that takes maybe 20 kilometers to cross from one side to the other. That is how big a neutron star is. 20 kilometers across, sometimes a little less. Roughly the width of a city. You could drive from one side of it to the other, in theory, in less than half an hour, if such a drive were physically possible, which it is not. But the scale is real. A neutron star is small. A neutron star is the smallest type of star in the universe. You could fit it comfortably inside the boundaries of any major metropolitan area on Earth. Let that sit for a moment. A star, the width of a city. And now I am going to tell you what it weighs. Inside that city-sized sphere, packed into a volume you could see in a single glance from a low-flying airplane, is more mass than our entire sun. More mass than the bright, burning, 865,000-mile wide ball of fire at the center of our solar system. All of it, compressed, squeezed, folded inward until it occupies the space of a small urban skyline. Take the sun. Take the thing so massive that every planet, every moon, every comet in our solar system orbits around it without question. Take the thing that contains 99.8% of all the matter in our solar system combined and shrink it. Shrink it down until it is smaller than the city you just pictured. That is a neutron star. The density numbers, when you write them out, almost stop meaning anything. 400 trillion times the density of water. A teaspoon of neutron star matter weighing 4 billion tons. A sugar cube of it, as I said earlier, outweighing every human being alive. These are not abstractions. These are not exaggerations for dramatic effect. These are simply what happens when you take the building blocks of matter and squeeze them past the point where the rules of ordinary chemistry can keep them separate. The neutrons are touching. There is no empty space inside the star. None. Every cubic centimeter is solid neutron matter. And here is where the story gets stranger. Because nobody knew these things existed for most of human history. Nobody could have known. Nobody could have predicted them. The math that suggested they might exist was first worked out in the early 1930s by physicists Walter Baade and Fritz Zwicky, who proposed, almost as a kind of theoretical curiosity, that a collapsed star made of neutrons might be possible. But it was just an idea. It was just numbers on a chalkboard. Nobody knew if such a thing actually existed out there in the universe. Nobody had ever seen one. That changed in the summer of 1967, in a muddy field outside the English town of Cambridge. A young postgraduate student named Jocelyn Bell was working under the supervision of an astronomer named Anthony Hewish. Together with a team of other students, they had spent 2 years hammering posts into the ground and stringing wire between them, building a strange and ugly radio telescope across 4.5 acres of farmland. The telescope did not look like the polished domes you might imagine when you think of an observatory. It looked like a field of fence posts and antennae. It looked unfinished, but it was tuned to listen for something specific. It was tuned to detect rapidly varying radio signals from deep space. Jocelyn Bell was the one assigned to read the paper printouts the telescope produced. Every day, the machine spat out roughly 30 meters of paper covered in inked squiggles, the recorded radio signals from across the sky. Her job was to look at it, all of it, by eye. She would unroll the paper, scan it for anything interesting, and mark anything that did not look like the expected noise. It was tedious work. It was solitary work. Most of what she found was nothing. Most of what she found was the ordinary background hum of the universe. And then, in November of 1967, she found something she could not explain. It was a small mark on the paper, a flicker in the signal, something that pulsed, not randomly, not chaotically, rhythmically. Every 1.33 seconds, exactly, a sharp burst of radio waves arrived from a specific point in the sky. 1.33 seconds, then again. 1.33 seconds, then again. The interval was so precise, so mechanical, so perfectly regular that Jocelyn Bell did not at first know what to make of it. Nothing in nature was supposed to behave like that. Nothing in the known universe could possibly pulse with the steadiness of a clock. She brought it to her supervisor. He thought, at first, that there must be a mistake in the equipment, some interference, some flaw in the wiring. They checked. There was no flaw. The signal was real. It was coming from out there. Somewhere far beyond the solar system, something was sending a metronome ticking through the cosmos. For a brief and slightly absurd period, the Discovery team gave the signal a nickname. They called it LGM-1. The letters stood for Little Green Men. It was a joke. Mostly, but underneath the joke was a real and not entirely comfortable question. Because the only thing the team could think of that might broadcast a signal of such mechanical precision was a civilization, a transmitter built by intelligent hands. The pulses were so regular, so artificial in their rhythm, that for a few weeks the small team in Cambridge genuinely had to consider the possibility that they had just intercepted a message from somewhere else. Then Jocelyn Bell found another one, in a different part of the sky, with a slightly different pulse rate, still perfectly regular, still mechanical, still ticking like a clock. And whatever else might be true, it seemed unlikely that two separate alien civilizations would happen to be broadcasting on the exact same frequency at the exact same time. The signals had to be natural. They had to be coming from some kind of object. The question was, what kind of object could possibly do this? The answer arrived within months. The pulses were coming from neutron stars. The theoretical objects proposed by Goddard and Zwicky decades earlier were real. They were out there. And the reason they pulsed was that they were spinning very, very fast. As a massive star collapses, the same effect that makes a figure skater spin faster when she pulls in her arms takes hold of the dying core. The star is conserving angular momentum. As it shrinks from a sphere larger than our sun to a sphere the size of a city, its rotation speed multiplies enormously. Some neutron stars rotate hundreds of times per second. A few rotate close to 1,000 times per second, and as they spin, they emit beams of radio waves from their magnetic poles, beams that sweep across the sky like the light of a cosmic lighthouse. Every time the beam passes Earth, our telescopes pick up a pulse, 1.33 seconds. In the case of Jocelyn Bell's first discovery, was simply the rotation period of a dead star somewhere out in the dark, turning on its axis, sending a flashlight beam across the galaxy at a rate that happened to point in our direction. This discovery would eventually win the Nobel Prize in Physics. The prize went to Anthony Hewish, her supervisor. Jocelyn Bell, the woman who had actually found the signal, who had stared at miles of paper for years to spot the anomaly, was not included. That is a story for another evening. But what matters here is that the universe had revealed something it had been hiding in plain sight for billions of years. Stars could die into something denser than anything matter was supposed to be allowed to become. And space was full of them. Astronomers now estimate that our galaxy alone contains somewhere between 100 million and 1 billion neutron stars. They are everywhere, quietly spinning, quietly waiting, most of them too faint to see, drifting through the dark between the brighter living stars. And tonight, you are going to fall into one. So picture yourself now. Picture yourself far out in interstellar space. The Earth is gone. The sun is gone. You are alone in a black so absolute it has no edges. You cannot tell whether you are upright or upside down because there is no up. There is no down. There is only distance, and the slow turning of the stars around you, and the silence that comes from being further from any planet than any human being has ever traveled. And ahead of you, still very far away, you can see it. It does not look like much. From this distance, it does not look like a star at all. It looks like a small, very pale point of light, perhaps a little blue, perhaps a little ghostly, no brighter than a dim candle held at the end of a long hallway. You could mistake it for an ordinary distant star if you did not know better. But you do know better. You know what it is. You know what it weighs. You know what it has already done to every atom that has ever come too close. You begin to drift toward it. You do not feel anything yet. There is no wind to push against you, no sense of falling, no awareness of motion in any direction. The distant point of light does not appear to grow. The stars around you do not appear to shift. To your senses, you are perfectly still, hanging in space, suspended, calm. You might even feel peaceful for a moment. The way you feel right before sleep, when the room has gone quiet and your body has finally given up the day. But something is already happening. Something inside you has already begun to change. Even at this distance, even with the neutron star looking no larger than a faint candle flame, the object ahead of you has already started to reach for you. Not your skin, not your bones. Something deeper. Something at the level of the atoms that make you who you are. The pull is so gentle you cannot detect it. Your senses, which evolved to notice the wind on a savanna and the footfall of a predator behind you, were never designed to feel what is happening now. But it is happening. It has already begun. And the hardest part, the part that will undo everything you understand about what it means to be a body in space, that part has not even started yet. The first thing to understand about your descent is how quiet it is. There is no sound out here. There has never been sound out here. Sound requires air, and there is no air in deep space, and there is certainly no air between you and the small, pale point of light that is your destination. Even if a supernova were happening directly behind you, even if a star were ripping itself apart at this very moment somewhere over your shoulder, you would not hear it. You would only see it, eventually, when its light caught up with you. The universe is enormous, and the universe is loud, and the universe is full of unimaginable violence. But to your ears, to the small, soft instruments evolution gave you for detecting the rustle of grass and the breath of a child, the universe is perfectly, completely silent. So this is what your fall sounds like. Nothing. Nothing at all. There is also no wind. You are moving, but there is nothing for you to move through. No air resists your motion. No friction warms your skin. The thin solar wind of charged particles that fills the space between stars is so diffuse, so impossibly sparse, that your body sweeps through it without registering its presence. You do not feel a breeze. You do not feel a chill. You feel nothing, and because you feel nothing, you do not feel that you are moving. This is the cruelest part of the early fall. Motion, as your brain understands it, is something you sense. You sense it through the pressure of a car seat against your back when the accelerator drops. You sense it through the rush of air past your face when you run. You sense it through the soft tug in your stomach when an elevator lowers you toward the ground floor. Your brain has spent your entire life calibrating itself to detect these tiny clues, these small physical signals that tell it where your body is going. Take those clues away, and your brain simply concludes that you are not going anywhere at all. So you feel still. You feel as though you are floating. You feel as though the small candle of light in front of you is doing the moving, drifting slowly closer of its own accord, the way a leaf drifts on a quiet pond. The truth is the opposite. You are the leaf. You are the thing in motion. And you are not drifting, you are falling. And you have been falling for some time now, and the speed at which you are falling has been increasing every second since the moment your fall began. Here is something you have known your whole life. When you drop a stone on Earth, it falls. It picks up speed as it falls. After 1 second of falling, it is moving at about 10 meters per second, the speed of a fast jog. After 2 seconds, 20 meters per second, the speed of a sprinting Olympian. After 3 seconds, 30 meters per second, which is faster than any human has ever run under their own power. The stone keeps accelerating. The pull of Earth keeps adding speed to it. If you dropped a stone from a tall enough cliff, it would eventually reach a terminal velocity, the speed at which air resistance balances gravity and stops the acceleration. For a falling human body in Earth's atmosphere, that terminal velocity is around 200 kilometers per hour. Fast, lethal if you hit the ground, but finite, bounded, limited by the air that surrounds you and by the gentleness, relatively speaking, of Earth's own gravitational pull. Earth's gravity, the gravity that holds you to your chair right now, the gravity that has shaped every step you have ever taken, is so mild compared to what is happening to you in this moment, that to compare them is almost meaningless. Almost. We are going to compare them anyway. On the surface of the Earth, an object falls with an acceleration of 9.8 meters per second every second. That number is called g. It is the standard by which all gravitational forces are measured. 1g is what you feel right now, sitting wherever you are sitting. 1g is the comfortable pressure of your body against the cushion. 1g is the reason your tea stays in your cup. On the surface of a neutron star, the acceleration due to gravity is approximately 200 billion g, 200 billion times stronger than what you have ever experienced. 200 billion times the force that holds your feet to the floor. There is no scale of human experience that can accommodate that number. Your brain hears it and rejects it. 200 billion is not a quantity you can imagine. It is not even a quantity you can fail to imagine. It is just a string of digits. But here is the thing. You are not yet on the surface. You are still very far away. You are, at this moment, perhaps 100,000 kilometers from the neutron star, roughly a quarter of the distance between Earth and the Moon. At this distance, the gravity pulling on you is much, much weaker than the surface gravity. It is still enormous by any sane measurement, but it is weaker. And because gravity from any object obeys an inverse square law, the closer you get, the stronger the pull becomes. Halve the distance, and the force quadruples. Halve it again, and it grows by another factor of 4. The pull is not linear. The pull is hungry. The pull accelerates its own acceleration. So here is what is happening to you right now as you drift toward that small, pale point of light. When your fall began, you were so far from the neutron star that the pull on you was barely measurable. You moved slowly. The increase in your speed was gentle, gentler even than the fall of a stone on Earth. For long minutes you might have been moving at a few meters per second, the kind of speed at which an ant crosses a kitchen floor. But every second, the pull grew. Every second, you were a little closer. Every second, the inverse square law tipped further in the neutron star's favor. The acceleration began to compound on itself. By the time you had been falling for a few minutes, you were no longer moving like an ant. You were moving like a car on a highway. Then a fighter jet. Then a rifle bullet. Then faster and faster and faster. There is no air to resist you. There is no terminal velocity. There is nothing to slow you down. There is only the pull, and the pull keeps growing, and your speed keeps climbing, and the small pale point of light ahead of you keeps brightening just slightly, slightly, slightly. By the time the neutron star is still 10,000 kilometers away, less than the diameter of the Earth, you have crossed a threshold that no human body was ever supposed to cross. You are now moving at a measurable fraction of the speed of light. Not 1%, not 5%, tens of percent. Your speed is now climbing toward numbers that physicists usually reserve for particle accelerators. The kind of speeds at which time itself begins to behave differently. The kind of speeds at which the rules of motion that worked for everything from horse-drawn carriages to space shuttles start to break down and require Einstein's equations to describe. And you feel nothing. You still feel nothing. That is the truly strange part. There is no sensation of acceleration, none. Because acceleration, as your inner ear understands it, requires something to push against. When a rocket accelerates a body, the seat pushes against the back of the astronaut. The astronaut feels the pressure. That pressure is what their brain interprets as movement. But gravity is different. Gravity does not push you. Gravity pulls every part of you at once, equally, with no resistance. Every atom in your body is being pulled at the same time, with the same force. Your inner ear is being pulled. The fluid inside your inner ear is being pulled. The hairs that detect motion in that fluid are being pulled. Everything is moving together. Nothing is being left behind. There is no resistance for your senses to register. This is why astronauts in orbit feel weightless, even though they are actually falling. They are in continuous free fall around the Earth. But because everything around them is falling at the same rate, they feel as though they are floating. You are in that same condition right now. You are in free fall. Free fall towards something that has the gravitational pull of 200 billion Earths, and your body cannot tell. It is one of the most peaceful sensations imaginable. You are weightless. You are silent. You are warm because there is no air to take heat away from your skin, although the radiation environment is starting to change, and we will come back to that. You are still you. Your heart is still beating. Your lungs are still breathing the small reservoir of air I am going to politely assume you have brought with you for the sake of this thought experiment. Your eyes are still working. You can still see the stars. You can still see the small pale point of light, which is now noticeably brighter than it was when you started, a candle that has grown into a small bright lamp. And while all of that is happening, while you sit there feeling perfectly normal and perfectly safe, you are being torn apart at a level your senses are not built to detect, because the gravity is not the only thing reaching for you. A neutron star is not just a dense object. A neutron star is one of the most strongly magnetized objects known to science. When a massive star collapses, the magnetic field lines that threaded through it during its lifetime do not vanish. They get compressed, just like everything else. They get crushed inward. They get squeezed into the same tiny volume that the neutron star itself occupies. And because magnetic fields, like all fields, become stronger when they are compressed into a smaller space, the magnetic field of a neutron star is amplified to levels that have no comparison in human experience. Earth has a magnetic field. You know this. Every compass needle that has ever pointed north is responding to it. The magnetic field of Earth is what protects you from the worst of the solar wind, what shapes the auroras at the poles, what allows certain birds and turtles to navigate across continents and oceans. The strength of Earth's magnetic field, measured in a unit called the Gauss, is about half a Gauss at the surface. Half. That is the number for the entire planet you live on. The field that has kept life on this world possible for 4 billion years. The magnetic field of an average neutron star is around 1 trillion Gauss. Some neutron stars, the most extreme members of the family, called magnetars, have fields 10,000 times stronger than that, 10 quadrillion Gauss. Numbers so large that the words to describe them lose meaning. If a magnetar were placed at the distance of the moon, its magnetic field would erase every credit card on Earth. It would scramble every hard drive. It would pull the iron out of your blood through your skin, from the distance of the moon. From 400,000 kilometers away, you are now much, much closer than the moon to your destination. So, what does a magnetic field of 1 trillion Gauss do to a human body falling toward it from 10,000 kilometers out? It does not do nothing. It does not, at this distance, kill you outright. Not in the way a sword kills, not in the way a fire kills, not in any of the ways your imagination is prepared to recognize as killing. What it does is more subtle than that. What it does is begin to change the rules by which your body is allowed to exist. Consider, for a moment, an atom, any atom in your body. The carbon atom at the end of one of your eyelashes will do. That carbon atom is not, despite what your school textbook may have suggested, a small solid ball. It is a fuzz of probability. At its center is a nucleus, a tight cluster of protons and neutrons. and around that nucleus is a cloud of electrons. The electrons do not orbit the nucleus the way planets orbit the sun. The electrons exist in regions of space called orbitals, fuzzy shells of probability where each electron is most likely to be found. These orbitals have shapes. Some are spherical, some are dumbbell-shaped, some are more complex. The shapes are determined by the rules of quantum mechanics, by the energies the electrons are allowed to have, by the way the electrons interact with one another and with the nucleus. The shapes of those orbitals are what make chemistry possible. Two oxygen atoms can bond with a carbon atom because their orbitals overlap in particular ways. Water has its specific properties because the orbitals in a water molecule are arranged at specific angles. The very structure of the proteins that fold inside your cells, the proteins that allow you to read this script and breathe this breath and form this memory, depends on the precise three-dimensional shape of electron orbitals. Take those shapes away, distort them, and you do not have chemistry anymore. You have something else. That is what is happening to you now. The magnetic field reaching across the void from the neutron star is so strong that it is overpowering the electromagnetic forces inside your atoms. The electrons in your body are no longer free to occupy their natural spherical orbitals. They are being squeezed. They are being compressed. The roughly spherical clouds in which they normally move are being deformed into thin, elongated cylinders stretched along the direction of the magnetic field. Imagine taking a balloon and pulling it from both ends until it becomes a long, thin tube. That is what is being done to every electron orbital in every atom of your body. You cannot feel this. There is no nerve in your body that can detect the shape of an electron orbital. The signal would never reach your brain because the chemistry of your nerves is also being changed. But it is happening. The molecules in your cells are no longer the molecules you were born with. The bonds between atoms are no longer behaving the way they did a moment ago. The hemoglobin in your blood, which depends on a very specific shape to carry oxygen, is no longer that shape. The enzymes in your gut are no longer those enzymes. The neurotransmitters in your brain are no longer those neurotransmitters. You are not yet dead. Technically, mechanically, by the strictest definition of the word, you are still alive. Your heart is still beating. Your neurons are still firing. The biological processes that define you as a living thing are still, for this brief and impossible moment, still operating. But the substances they operate on are no longer the substances they were designed to operate on. Every cell in your body is performing a function for which it was never built, on materials that no longer obey the chemistry that made them possible. It is a strange kind of death. It is not the death of the body. It is the death of the rules by which the body was allowed to be a body in the first place. And here is the part I find the hardest to describe. You are still conscious. Probably, insofar as consciousness can exist at all under these conditions. The atoms in your brain are deforming, but they are deforming together, in concert, all at the same time and in the same way. The chemistry of your thoughts is changing, but it is changing uniformly. So perhaps you still feel like yourself. Perhaps you still feel curious. Perhaps you are still watching the small pale point of light grow slowly larger, brightening from a candle to a lamp, from a lamp towards something like a street light, and perhaps a part of you is still wondering, in some abstract, distant way, what it will look like when you finally get close enough to see it properly. You will get close enough, soon, sooner than you think. You should know that the time you have left, measured in the way you used to measure time on Earth, is now very short. The acceleration is still growing. You are falling faster every second, and every second the pull grows stronger, and every second your speed climbs higher up the impossible ladder toward the speed of light. The distance from where you are to the surface of the neutron star is closing not in hours, not in minutes, but in seconds, real seconds, a small number of them. A few seconds. That is what you have. A few seconds before the next phase begins. And the next phase is going to do something to your body that no force in the natural universe is supposed to be able to do. The magnetic field has changed your chemistry. The gravity has changed your motion. But neither of those things comes close to what is about to happen next. Because so far, the gravity has been pulling all of you equally. Every part of you has been falling at the same rate. That is why you have not felt your descent. That is why you have remained, in a sense, peaceful. But that is about to end. Because the closer you get to the neutron star, the more sharply the gravity will begin to vary from one part of your body to another. Your feet, which are now slightly closer to the star than your head, are about to begin falling faster than your head. And the difference between those two speeds is about to become very, very important. You are still you, for now. You are still a body. You are still a single coherent shape in space, falling toward a candle that has become a lamp that is now becoming a small, bright sun. You are still alive in any sense of the word that matters. You are about to stop being any of those things. But that part has not begun yet. Think for a moment about what stretching feels like. It is one of the gentler sensations your body knows. The slow, long pull of a yawn that catches you off guard in the late afternoon. The reach across a bed in the morning when you are not quite awake, your fingers extending toward a pillow that has drifted to the far edge during the night. The lengthening of your spine when you stand up after sitting too long. Stretching is comfort. Stretching is the body releasing tension it did not know it was holding. There is a softness to it, a quiet pleasure. Children stretch. Cats stretch. The first thing many of us do upon waking is stretch. It is one of the most innocent words in the language. I am going to ask you, in a moment, to think about it differently. Because what is about to happen to you as you fall toward the neutron star is going to be described by physicists using a single, calm, scientific word. They will call it stretching. They will call it tidal stretching, to be precise, or sometimes, more colourfully, spaghettification. Both of those terms sound almost playful. Both of them invite you to imagine something gentle, something elastic, something that pulls and gives and pulls again. Neither of them, neither word, neither phrase, comes close to what is actually about to occur. What is about to occur is not stretching in any sense your body has ever known. What is about to occur is the universe taking your shape apart, atom by atom, along a single direction in space, with a force so absolute that no material in existence is strong enough to resist it. Let me show you the geometry. You are falling feet first. This is how the thought experiment has set you up. Your feet are pointed toward the neutron star, your head is pointed away from it, and your body is hanging there in space like a diver, suspended forever at the top of a plunge. The neutron star is below you. Below, in the sense that gravity now defines down. There is no other below anymore. There is only the direction of the pull. And here is the small fact that ruins everything. Your feet are closer to the neutron star than your head. It is a trivial observation, almost embarrassing in its obviousness. Of course your feet are closer. Your feet are at one end of your body, your head is at the other, and you are roughly 1 3/4 meters long. Your feet, in this moment, are somewhere around 1 3/4 meters closer to the surface of the star than the top of your skull. That is the distance between them. That is the difference. A small thing by any normal measure. The length of a tall door, the height of a child, the reach of an outstretched arm. But gravity does not care about normal measures. Gravity cares about distance, and gravity cares about distance with a kind of mathematical ferocity that almost no one truly absorbs until it is too late. Because gravity from any object follows that inverse square law. Halve the distance, quadruple the force. Quarter the distance, multiply the force by 16. And near a neutron star, where the surface gravity is 200 billion times that of Earth, even very small differences in distance produce very large differences in force. So your feet are being pulled by the star, and your head is also being pulled by the star. But your feet are being pulled harder. How much harder? That depends on how close you are. Far out, when you were 100,000 kilometers away, the difference between the pull on your feet and the pull on your head was so small that no instrument could have measured it. The two forces were essentially equal. Your body fell as a single coherent object. Closer in, at 10,000 kilometers, the difference became measurable but still gentle. A small tugging sensation, maybe, if your nerves were calibrated to detect it. Closer still, at 1,000 kilometers, the difference became something a human body would notice. A pulling, a discomfort, the kind of feeling you might mistake for the early sign of a cramp. You are not at 1,000 kilometers anymore. You blew past that distance some seconds ago. You are now within a few hundred kilometers of the surface. And the difference in gravitational pull between your feet and your head has stopped being subtle. It has stopped being noticeable. It has become catastrophic. Your feet are being pulled toward the star with a force greater than the strength of your own body to hold itself together. Read that sentence again, because the language is doing very little of the work that the reality requires. The force pulling on your feet is greater than the chemical bonds holding your tissues to themselves, greater than the cohesion of your bones, greater than the strength of your muscles, your tendons, your skin, greater than anything biology has ever produced, greater than the force required to tear steel, greater than the force required to shatter diamond, greater, in the limit, than the force required to crush an atom into something that is no longer an atom. The pull on your feet is stronger than the pull on your head, and the difference between those two pulls is more than your body can survive. So your body stops being a body. Not all at once. Even now, even this close, there is a sequence. There is a geometry. The thing happens in a particular order, and the order matters, because it tells you something about how the universe ends a human being. It begins at the soles. The cells of your feet are the closest to the star, and so they are being pulled hardest. The cells of your ankles are slightly farther, and so they are being pulled slightly less. The cells of your knees, less still. The cells of your hips, less again. Your head, the part of you that is farthest from the surface, is being pulled the least of all. This means that every part of your body is moving toward the star at a different speed. Your feet are accelerating faster than your shins. Your shins are accelerating faster than your thighs. Your thighs are accelerating faster than your torso. And the parts of you that are accelerating faster are pulling away from the parts of you that are accelerating slower. So your body begins to lengthen. Not in the gentle sense. Not in any sense your nervous system was built to interpret. Your feet are being torn away from your ankles. Your ankles are being torn away from your shins. The tissues of your legs are coming apart, separating along the line of the pull, the line that connects every part of you to the surface below. You are being unmade in a single direction, stretched, drawn, pulled into a thin, lengthening shape, like dough being rolled, except no dough has ever been pulled by a hand this strong. This is the moment physicists call spaghettification. The word was popularized by Stephen Hawking, who introduced it in the context of black holes, but the same process happens here, near a neutron star, at distances where the tidal forces become extreme enough to overwhelm the material strength of any object falling in. Spaghettification. The word is almost a joke. The reality is anything but. Your body, The single shape that has carried you through every day of your life is no longer a single shape. It is a column, a long, thinning, accelerating column of what used to be you, being drawn down toward the star like water down a drain, except faster than water has ever moved, and through a drain that does not exist except as the direction of falling. Your skin is stretching past the point where skin can stretch. Your bones are fracturing, then powdering, then atomizing. Your blood is no longer in your veins because your veins are no longer veins. The shape of you is dissolving into the line of the pull, and the further you fall, the worse it gets. The closer you get to the surface, the steeper the gradient becomes. The difference in pull from one end of your stretched column to the other becomes more extreme by the millisecond. The column thins, the column lengthens. Your atoms, the atoms that built every part of you, the carbon and the calcium and the oxygen and the hydrogen and the small precious traces of iron that once filled your blood, are now spreading out along a line that points directly at the surface below. You are being turned into a stream, a pencil-thin stream of matter, accelerating toward a sphere it has not yet touched. I need to stop here. I need you to stop with me, because something else is happening at the same time as this, something that almost no one talks about, something that complicates the entire picture of what your fall actually looks like, depending on who is watching it. Let me bring you back, for a moment, to the idea of distance. There is another observer in this scene, not you. Imagine a friend. Imagine someone you love, watching from far away, watching from a safe vantage point, millions of kilometers from the neutron star, watching through a telescope so powerful and so perfect that they can see the small shape of you as you fall. They have been watching since the beginning. They saw you when you were a distant figure drifting in deep space. They saw the candle of the neutron star grow into a lamp. They watched you accelerate. They watched your speed climb. They watched you become a streak. And now, as you are within seconds of the surface, they are watching something very strange begin to happen. You are slowing down, not because the pull is weakening. The pull is not weakening. The pull is, by every honest measurement, growing. But to your distant friend, watching through their telescope, the streak of you is no longer accelerating, it is hovering. The closer you get to the surface, the slower your fall appears to be. The motion is dragging out. Your descent, which had been compressing in time, is now expanding in time. Each second of your fall, from their perspective, is taking longer than the second before it. The whole picture is becoming sticky, slow, almost frozen. This is not an illusion. This is not a trick of their telescope. This is real. This is time itself, behaving the way Einstein said time would behave, under conditions of extreme gravity. The theory has a name, general relativity. It was published in 1915, and it has been confirmed every single year since then, in every test physicists have been able to devise. One of its strangest predictions is that time does not move at the same rate everywhere. Time moves slower near massive objects. The stronger the gravity, the slower the time. On Earth, the effect is so tiny that you would never notice it unaided. Atomic clocks at the top of a mountain tick very slightly faster than atomic clocks at sea level. The difference is real. The difference is measurable. The difference is also vanishingly small. But near a neutron star, the effect is not small. The effect is enormous. The surface of a neutron star is so massive, so compact, so deep in its own gravitational well, that time near it crawls compared to time far away. For every second that passes on the surface, your distant friend, watching from millions of kilometers out, might experience several seconds, or many seconds, depending on the exact mass of the star. And the closer you fall, the worse the discrepancy becomes. You are not just falling through space, you are falling out of synchronization with the rest of the universe. Your friend, then, sees you as a slow, elongating streak. The streak grows fainter because the light coming from your body is being stretched too, its wavelengths drawn out, its colors shifted toward red, and then deeper red, and then into wavelengths their telescope can no longer see. You are not just slowing, you are dimming, you are reddening, you are fading. From your friend's perspective, you never quite arrive. The closer you get to the surface, the more time stretches, until in the most extreme limit, time appears to nearly stop. A version of you, from their point of view, is suspended forever a few meters above the star, frozen mid-fall, ghostly and red and almost gone. But from your own perspective, the perspective of the falling body, none of this is happening. You feel no slowness. You feel no time dilation. Time, for you, is moving as it always has, second by second, exactly the way time moves when you are at rest in a quiet room. You are accelerating. You are arriving. You are streaming toward the surface in a thin column of disassembled atoms, and from your point of view, the whole event is happening at terrifying speed. The end is coming fast. The end is coming in fractions of a second. There is no slowing. There is no freezing. There is only the rush. So which version is real? The one frozen above the surface, drawn out in stillness for what could be hours of external time, slowly reddening into invisibility. The one falling, finishing the descent in moments, arriving at the star with a swiftness no one watching could ever witness. Both are real. Both versions describe the same event from different points in space. There is no objective answer to the question of which is the true story, because in general relativity there is no single true story. There are only stories, each one valid within its own frame of reference, each one as true as any other, none of them able to be reduced into a single answer. Which version is you? Are you the streak that ends in an instant? Are you the ghost that lingers forever, a few meters above the surface, never quite touching down? You are both. You are neither, depending on who is watching, depending on where they stand, depending on the angle of the universe from which they cast their gaze. The version of you that exists for your friend is not the same as the version of you that exists for yourself. There is no contradiction. There is no error. There is only a universe in which two things, equally real, can describe the same event in ways that look completely different from the outside. Let that breathe. Now, let me bring you back to the inside of the experience, to the version of you that is still falling. Because in your own frame of reference, the surface is no longer far away. The surface is no longer abstract. The surface is no longer hidden in the brightness of the candle that grew into a lamp, that grew into a small sun. The surface is now directly beneath you, and it is rising to meet you, and for the first time in your descent, you can see it clearly. It does not look like anything you have ever seen. You expected, perhaps, something like the sun, something boiling, something turbulent, something with flares licking up from its limb, and storms churning across its face. That is what most stars look like. That is what the dying star that produced this object would have looked like in its final years. This is not that. This is smooth. The surface of a neutron star is the smoothest object known to science. So smooth that astrophysicists have calculated the height of its tallest mountains, and those mountains, the highest points on the entire surface of the star, are roughly the height of a sheet of paper, a few millimeters. Less, in some cases. The crust of a neutron star is so dense, and the gravity holding it down is so absolute, that nothing on its surface is allowed to rise more than a tiny fraction above the rest. The whole sphere is polished by its own weight, sanded flat by gravity itself, smoother than any mirror humans have ever ground, smoother than any planet, smoother than anything that exists in the natural universe. So what you see as you fall is a sphere of impossible perfection, a pale glowing curve, faintly luminous, the color of something between white-hot iron and the deep blue heart of a flame. It does not flicker, it does not boil, it does not move in any way your eye can follow. It just sits there beneath you, vast and silent and serene, while you stream toward it in your column of dissolving atoms. And somewhere far away your friend watches your slow ghost hang frozen in the red light of a vanishing fall. You have never been this close to anything more alien. You have never been this close to a thing that should not be possible. And the strangest part is that you have not yet reached it. The surface is still beneath you. You are still falling. The thinning column of what used to be your body is still pointing down, still streaming, still descending toward a sphere whose smoothness defies every intuition you have ever had about the shape of stars. You are about to touch it. Not in the way you have touched anything before, not in any way that touching was ever supposed to mean. But that part is still ahead. Let me ask you to imagine something that may not be entirely possible. Let me ask you to imagine that you still have eyes. In any honest reckoning of what is happening to your body at this point in the fall, you do not. The column of atoms streaming toward the surface no longer contains anything that could be called a body in the ordinary sense, and certainly no eye, no retina, no optic nerve, no fragile little camera designed by evolution for the gentle business of looking at sunlit grass and the faces of people you love. All of that is gone. All of that was undone in the long stretching that preceded this moment. But suppose, for the purposes of this thought, that some small part of you could still see. Suppose that the visual experience of falling continued, even after the physical possibility of it had ended. Suppose that consciousness, in whatever form it now takes, could still register light coming in from the universe around you. What would you see? You would see something that no human being has ever seen, and no human being has ever been built to see, and no human being's brain was ever designed to interpret. You would see the universe bent. The first thing you would notice is that the stars are wrong. Before your fall began, the star field around you was distributed evenly. Stars to your left, stars to your right, stars above you, stars below you, in every direction the slow, scattered light of a galaxy at rest. The pattern was familiar in the way that any random pattern becomes familiar after long exposure. There was a kind of comfort to it. The stars were where they should be. They were where they always had been. They were where any human ancestor, standing anywhere on Earth, on any clear night for the last several 100,000 years, would have seen them. That pattern is now broken. The stars in front of you, the stars in the direction of your fall, are no longer where they should be. They have shifted. They have crowded together. They have piled up around the edge of the neutron star, like water rushing around the rim of a drain. The stars that you would expect to see far behind the neutron star, hidden by its bulk, completely blocked from view, are now visible, not at the edges of the star, through it, around it. In front of it, in some sense that defies what the word in front can mean. You are looking at the back of the star and the front of the star at the same time. This is not a hallucination. This is not your dying optic nerve playing tricks on you. This is geometry. This is the literal shape of space near a very massive object, and the literal path that light is forced to take when it travels through that shape. Light does not move in straight lines near a neutron star. Light cannot move in straight lines near a neutron star, because the lines themselves have been bent. The space that the light moves through is curved, and the light, having no choice in the matter, follows the curve. A star sitting directly behind the neutron star, in the opposite direction from you, on the far side of all that mass, is sending its light outward in every direction the way all stars do. Some of that light, the light heading directly away from you, you would never see. But the light heading sideways, The light heading off into what should be unrelated regions of space is being captured by the curvature near the neutron star, bent into a curve and redirected toward your eyes. The light that should have missed you by trillions of kilometers is being delivered to you, gift-wrapped by the geometry of the universe. You are seeing things you should not be able to see, because the universe is showing them to you through a lens it never asked permission to grind. The shape of what you see, then, is strange. The neutron star sits at the center of a ring of light. The ring is not solid. The ring is made up of distorted, stretched images of stars, each one smeared into an arc, each one looped around the dark sphere in front of you, each one belonging to a star that you would normally have to turn completely around to see. The star field behind your back is also painted, in some warped way, around the edges of the sphere. The universe has folded itself around your destination. If you are still capable of having a thought at this point, the thought is this: the sky has become a halo. This is gravitational lensing. And the man who predicted it, more than 100 years before you began your fall, was Albert Einstein. Einstein did not arrive at the idea casually. He had spent the better part of a decade, from 1905 to 1915, building the mathematical scaffolding that would eventually become the general theory of relativity. The work was slow. The work was painful. The work involved teaching himself areas of mathematics he had not previously known existed, then using them to describe a universe in which gravity was no longer a force in the old Newtonian sense at all. In Einstein's picture, gravity was geometry. Mass curved space. Curved space told other objects how to move. Light, having mass equivalent in the form of energy, would also bend along the curve, even though light has no rest mass in the traditional sense. The bending would be slight near most objects. The bending would be measurable near very massive ones. When he published the full theory in 1915, almost no one believed him. The mathematics was forbidding. The conclusions were strange. The notion that space itself could be curved was, to most physicists at the time, a kind of poetry, possibly elegant, possibly meaningless. It took an eclipse to settle the question. In May of 1919, a British astronomer named Arthur Eddington led an expedition to the island of Principe, off the west coast of Africa, to observe a total solar eclipse. A second team went to Brazil. The plan was simple and audacious. During the eclipse, the moon would block the disk of the sun, and the stars normally hidden by daylight would become briefly visible near the solar limb. If Einstein was right, the light from those stars, passing close to the sun on its way to Earth, would be bent slightly by the sun's gravity. The stars would appear to have shifted from their normal positions. The shift would be small, a tiny fraction of a degree, but it would be measurable, and it would be in the exact direction and magnitude that Einstein's equations predicted. The skies cleared just enough. The photographs were taken. The plates were developed and measured back in England over the following months. And in November of 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London, the result was announced. The stars had moved. They had moved by the amount Einstein had said they would move. Space, the room in which everything in the universe sits, was curved, and the sun was curving it, and the light of distant stars was bending in just the way the theory had predicted. The next morning, Einstein was on the front page of every major newspaper in the world. He went to bed an obscure German physicist and woke up the most famous scientist alive. The eclipse had confirmed something stranger than fiction. Gravity was not a force pulling on light. Gravity was the shape of the space the light moved through. That was the sun. That was the gentle bending caused by the gravity of an ordinary star. What you are now seeing is the same effect, but multiplied by orders of magnitude that the team on Principe could not have imagined. The neutron star beneath you is bending light, not by a fraction of a degree, but by entire visible arcs across your field of view. Some of the light reaching your eyes has wrapped almost all the way around the star before completing its journey. There are even rays of light, in principle, that could orbit the star one full time before escaping. The whole geometry of seeing has been remade. You are inside an optical phenomenon that Einstein, who started this with chalk and patience and a willingness to believe in invisible curves, only ever wrote about in equations. And below all of this seeing, below the halo and the bent stars and the impossible visual logic of your descent, lies the surface itself. You are close enough now to study it. You are close enough now to see what it actually is. Most people, when they think of the surface of a star, picture flame, picture turbulence. Picture the boiling photosphere of the sun, with its granulation and its sunspots, and its arching prominences, and its ceaseless seething motion. This is what stars do. Stars are gas. Stars are plasma. Stars are restless. The surface beneath you is not gas. The surface beneath you is solid. The crust of a neutron star is a solid lattice, a crystalline solid in the strict sense of the word. Atoms locked together in a regular geometric pattern, like the molecules in a piece of quartz or the silicon in a microchip, except packed together at densities that no quartz, no diamond, no laboratory-grown crystal on Earth could ever approach. The atoms in question are mostly iron nuclei, the heavy remnants of the original star's final fusion stages, and they are arranged in a tight, regular structure with electrons swimming through the gaps between them like fish moving through coral. The density of this crust is on the order of 1,000,000 times the density of any solid you have ever held. A piece of it, the size of a marble, would weigh as much as a battleship. But here is the part of the surface that I find the strangest. The part that almost no one anticipates when they first learn about these objects. There are mountains. Mountains on a neutron star. Geological features. Slight upward bulges in the crystalline iron lattice. Lifted by the residual heat of formation, by the slow internal pressures of the star's interior, by the deep magnetic stresses that thread through the crust. These mountains are not imagined. Astrophysicists have studied them. There are papers about them. There is genuine ongoing research into the question of exactly how tall such a mountain can grow before it collapses back into the smoothness of the surrounding crust. You hear the word mountain and you think of something. You think of Everest. You think of the Alps. You think of the slow uplift of continental plates over millions of years, and the snow caps that gather at the peaks, and the small, slow rivers that fall away from the summits in spring. You think of something high, something that pierces the sky, something that you would have to climb. The tallest mountain on the surface of a neutron star is roughly the height of a sheet of paper. Read that again, because it is one of the most absurd sentences in all of astronomy. A few millimeters, possibly less, depending on the star. The tallest peaks on the entire surface of one of the densest objects in the universe are smaller than the thickness of your fingernail. The whole sphere is so close to perfectly smooth that if you scaled a neutron star up to the size of Earth, its tallest geological feature would still be a few centimeters. A small bump, a wrinkle, a pebble underfoot. The reason is gravity. The same surface gravity that is currently tearing your body apart along the line of your fall is also pressing down on every feature of the star itself, leveling everything, flattening everything, smoothing every irregularity. Any mountain that tried to grow taller than a few millimeters would be crushed back into the crust the moment its height exceeded what the local gravity could sustain. The crystalline iron is strong, by terrestrial standards, immensely strong. But no material is strong enough to stand tall against 200 billion G. So the sphere beneath you is a polished thing, a precisely sanded ball of impossible density with its tiny millimeter-sized hills, with its silent crystalline plains, with its surface that mirrors the curved halo of the distorted sky above it. A still object, a motionless object, a finished thing, except that it is not still, and it is not motionless, and it is not, in any meaningful sense, finished, because there is sound down there. This is, perhaps, the strangest claim in the entire field of neutron star physics, and it is also entirely true. The surface of a neutron star, despite being a solid crystalline lattice in the vacuum of space, despite being completely beyond the reach of any ear, despite being unable to transmit sound to the outside world by any conventional means, is itself vibrating, constantly, in every direction, with energies that no earthly musical instrument has ever come close to producing. The vibrations have a name: starquakes. They are the neutron star equivalent of earthquakes, except that what is shaking is not the soft crust of a rocky planet, but the absurdly dense crystalline iron lattice of a collapsed star. They occur because the star is slowing down over time. The rotation rate, which can be hundreds of revolutions per second, gradually decreases as the star sheds energy. As it slows, its shape changes, very slightly, very subtly, becoming less oblate, more nearly spherical. The crust, which is locked in by its own crystalline structure, cannot smoothly adjust to the changing shape. It resists. It builds up stress. It builds up more stress. And then, suddenly, it cracks. When the crust cracks, a starquake ripples through the surface. The vibrations are very fast, very high in frequency, and they travel through the crystalline iron at enormous speeds. They cause the entire star to ring in the technical sense. The whole sphere oscillates, like a bell, except that the bell is denser than anything that has ever been forged in a foundry, and its tone, if you could somehow translate the oscillation into a sound, would lie far outside the range of any human ear. The vibrations occur at frequencies thousands of times higher than the highest note a piano can play. There is, in the most literal sense, music on the surface of a neutron star. There is rhythm, there is resonance, there are modes of vibration, harmonic structures, overtones, the same physics that allows a violin string to produce a particular note when bowed. The star sings. The star sings to no one. The star has been singing for as long as it has existed, and it will keep singing for as long as it goes on existing, which is to say, longer than the sun, longer than the earth, longer, in all likelihood, than any living being that will ever evolve in this galaxy. You are about to be added to that song. The atoms that used to be you, the carbon and the calcium and the oxygen and the iron, are about to join the lattice. They are about to become part of the music, but not yet. You are still falling, still streaming, still suspended in the strange overlapping geometries of light and gravity and time. The surface is still beneath you. From your point of view, the surface is moments away. From your distant friend's point of view, the surface is forever away, and you are a slow red ghost hanging just above it, drawn out across time, fading. Neither of those views is wrong. Neither is more real than the other. What is real is the sphere. What is real is the curved halo of bent starlight. What is real is the silent, ringing crystalline crust beneath you, with its millimeter mountains and its impossible smoothness, waiting to receive whatever is left of the thing that began this fall as a body. The surface is rising, or you are descending, or both, in some sense that the words can no longer quite hold. You have not yet touched it, but the touching is close, closer than anything has ever been to anything in your life. And what is about to happen on the other side of that surface, in the dark below the crust, is stranger still. I have to be honest with you now. Everything I have described until this moment, everything about the death of the massive star, the spinning lighthouse beam discovered in Cambridge, the bending of light around the polished sphere, the millimeter mountains, and the silent ringing crust, all of that is well-established science. All of that has been confirmed by observation, by mathematics, by decades of careful work performed by astronomers and physicists who have built their understanding from the outside in. They have measured these stars. They have timed their pulses. They have watched two of them collide. They have triangulated their masses and modeled their crusts, and listened with their gravitational wave detectors to the ripples those crusts send through the fabric of space itself. But once we cross the surface, once we step past the crystalline iron crust and into the interior, the certainty thins. There are no probes down there. There never have been. There never will be. No instrument humans have ever built, no instrument humans could ever conceivably build, could survive a journey to the inside of a neutron star and report back what it found. The pressures are too extreme. The forces are too absolute. The interior of a neutron star is one of the very few environments in the universe that lies permanently beyond the reach of direct experimental verification. We can never go there. We can never send anything there. We can only infer, from the behavior of the stars outside, what its inside might be. So what follows is the best understanding physics offers. It is not certainty. It is reasoned theory, tested against every observation we can make from beyond the surface, refined by every gravitational wave we have detected, narrowed by every neutron-star merger we have watched unfold in the deep sky. It is our best current picture. It is also a picture that may yet be revised. Some of what I am about to describe could turn out to be wrong, and some of it could turn out to be right, in ways we do not yet fully appreciate, and some of it could turn out to point toward physics we have not yet discovered. With that said, with that humility in place, here is what we believe lies below. The first layer, the outer crust, is where you have just entered. You crossed it as the column of atoms streaming downward, and the column met the lattice of iron nuclei, and the meeting was the kind of event that does not have a good word in any human language. The atoms that used to be you have been pressed into the existing crystalline structure, added to it, absorbed by it, integrated into the polished surface of the star at a rate of arrival so violent and so complete that no boundary remains between what used to be you and what was already there. The transition is not a collision. The transition is an inclusion. The lattice has accepted you. The star has gained mass by some very small amount, equal to the mass of the human being you used to be, and that mass is now part of its total weight, part of its rotational moment, part of its silent ongoing music. The outer crust extends downward for roughly 1 kilometer or so. Throughout that depth, the structure remains crystalline. The iron nuclei sit in their regular pattern, packed at densities that increase steadily the deeper you go. Near the surface, the density is around 1 million times that of ordinary iron on Earth. A few hundred meters down, it is 10 million times. 1 kilometer down, hundreds of millions of times. The crystal does not change in any obvious way, but the spacing between the nuclei grows tighter, and the pressure squeezes the electrons into ever more confined paths, and the whole arrangement becomes more and more strained. And then, somewhere around 1 kilometer beneath the surface, the structure begins to change in a way that has no parallel anywhere in ordinary matter. The pressure becomes so extreme that electrons, which until this point have been swimming through the gaps in the lattice as a kind of degenerate sea, begin to be pushed into the protons inside the iron nuclei. They merge. The electron and the proton combine into a neutron, releasing a particle called a neutrino in the process, and the neutrino streams outward and escapes the star at the speed of light, carrying energy away with it. Inside the iron nuclei, the proton population is being replaced by neutrons. The atoms themselves, the basic units of all chemistry, are being chemically transformed by sheer pressure into something neutron-rich, something that on Earth could not exist for more than a fraction of a second before falling apart. The deeper you go, the more this happens. The nuclei grow heavier in neutrons. They become unstable by any earthly standard, but the pressure here holds them together. At some critical depth, the nuclei become so full of neutrons that they cannot hold any more. The neutrons begin to leak, they drip out. They escape the confines of the nuclei and spill into the gaps between them. This is called neutron drip, and the depth at which it begins marks the boundary between the outer crust and the inner crust. Inside the inner crust, the picture grows still stranger. The atomic nuclei still exist, but they are now sitting in a sea of free neutrons that fills all the space between them. The nuclei themselves take on increasingly bizarre shapes as the pressure climbs. They are no longer simply spherical. They begin to stretch into rods. The rods elongate. They merge into slabs. The slabs interconnect. The whole structure at this depth has been given a name that almost embarrasses the physicists who use it. They call it nuclear pasta. The shapes really do resemble pasta. Spheres at one depth give way to long, thin rods that look like spaghetti, which give way to flat sheets that look like lasagna, which give way to honeycombs that look like nothing in any human kitchen at all. The whole layer is a kind of cosmic kitchen in which the basic structures of matter have been rolled out into shapes that exist nowhere else in the known universe. This nuclear pasta is itself a solid, a bizarre solid. A solid in which the basic units are not atoms but distorted nuclear shapes, floating in a sea of neutrons that are themselves bound together by forces that human technology has never been able to replicate. The pasta is thought to be the strongest material that exists anywhere, tens of billions of times stronger than steel, by some calculations. So strong that if a piece of it could somehow be brought to the surface of the Earth intact, it would resist any force we know how to apply to it. The pasta layer is thin, a few hundred meters, perhaps a kilometer at the outside, and then, beneath it, the nuclei dissolve entirely. There are no more nuclei. There is no more crystalline structure of any kind. What lies below is something that has never been seen by human eyes and never will be seen by human eyes. It is an ocean of pure neutrons. Imagine, if you can, a fluid in which every single particle is a neutron. No atoms, no protons, no electrons, just neutrons, packed shoulder to shoulder, filling the space the way water fills a swimming pool, except at densities so extreme that the comparison fails the moment you start to think about it. The fluid extends for kilometers, possibly for most of the radius of the star. Most of the mass of a neutron star, by current estimates, is contained in this layer. Most of what a neutron star is, in the most literal sense, is this ocean. And the ocean does not behave like an ordinary fluid. It is a superfluid, a state of matter in which the rules of friction, the rules of viscosity, the rules that govern the way every fluid you have ever seen behaves, simply do not apply. A superfluid flows without resistance. If you could somehow set a current moving inside a superfluid, the current would continue, undiminished, for as long as the conditions were maintained. There is no drag, there is no slowing, there is no decay. The fluid moves as if it were a single thing, a single coordinated entity, every neutron in step with every other neutron, all of them executing the same quantum mechanical dance at the same time. This sounds like magic. It is not. Superfluids have been created in laboratories on Earth, in tiny amounts, at temperatures very near absolute zero. Liquid helium becomes a superfluid below about 2 degrees above absolute zero. It does strange things. It climbs up the walls of its container. It flows through openings, too small for any ordinary fluid to pass. It forms quantized vortices, little tornadoes that spin forever without slowing. All of this has been seen in laboratories. All of this has been measured. Superfluidity is not a theoretical curiosity. It is a real, well-documented state of matter. What is theoretical is that the inside of a neutron star, despite being unimaginably hot by everyday standards, despite being at temperatures of millions of degrees, is also, in the relevant sense, cold enough for its neutrons to fall into a superfluid state. The reason has to do with how strongly the neutrons interact with each other and with the particular quantum mechanical properties of how they pair up at high density. The math says yes. The math has said yes for decades. And the math is supported by observations of neutron star cooling rates, observations of starquake recoveries, observations of the way certain neutron stars rotate and slow down, all of which fit the superfluid picture in ways that ordinary models cannot explain. So most of the star is an ocean of frictionless neutrons, an ocean that flows without flowing, that moves without moving, that is at once liquid and crystalline depending on which property you look at. An ocean in which the atoms that used to be your fingertips are now part of the medium itself, dissolved into the broader fluid, indistinguishable from any other neutron in any other part of the star. And below the ocean, at the very center, lies the core. This is where the certainty ends entirely. The pressures inside the core of a neutron star are higher than anything that has ever existed or ever will exist outside of a black hole. The densities are higher than anything that has been produced, even in the most violent particle accelerators on Earth. What matter does, under those conditions, is not known. What matter is, under those conditions, is not even a well-defined question. There are theories. The most conservative theory is that the core is simply more of the same. More neutrons, packed even more tightly, possibly behaving as an even more extreme version of the superfluid above. The neutrons hold together. They remain neutrons. They are just compressed beyond any earthly comprehension. A bolder theory says that the neutrons themselves break apart. A neutron, you may remember, is not a fundamental particle. A neutron is a composite. It is built out of three smaller particles called quarks, held together by a force called the strong nuclear force. Under normal conditions, quarks are never free. They are always bound inside protons and neutrons and other particles. The strong force is so strong that pulling two quarks apart actually creates a new pair of quarks in the gap, like a stretched rubber band snapping into two pieces, each piece carrying its own ends. Quarks have never been observed in isolation. They are not believed to be capable of existing in isolation under ordinary circumstances. But the inside of a neutron star is not ordinary circumstances. At the densities theorized for the core of a neutron star, the neutrons may be pressed so tightly together that they begin to overlap. The boundaries between one neutron and the next begin to blur. The quarks inside them are no longer cleanly assigned to one neutron or another. They begin to mingle. They begin to move freely across what used to be the borders between particles. And at some critical density, the very concept of a neutron may dissolve entirely. What remains is a soup of quarks, a material in which the building blocks of protons and neutrons exist as free particles, swimming in a medium that has no analog in any laboratory experiment ever performed. This is called quark matter, and it is one of the most actively studied theoretical states in modern physics. It has never been directly observed. Whether it exists inside actual neutron stars is one of the great open questions of the field. Recent observations of unusually massive neutron stars and unusually compact ones are slowly narrowing the possibilities, but the question is not yet settled. And quark matter is not even the strangest possibility. Some theorists have proposed that the cores of certain neutron stars may contain something called strange matter. Strange matter would be a state in which not just up and down quarks, the kinds that build ordinary protons and neutrons, but also a third type, called the strange quark, become abundant in equal proportion. Such matter, if it exists, may be more stable at high density than ordinary nuclear matter. It may be the true ground state of matter, with everything else just being a long-lived metastable mistake. The implications of that, if it is true, are profound enough that physicists have been arguing about them for almost half a century. Other theorists suggest that the core may host even more exotic phases. Color superconductivity, a state in which quarks pair up the way electrons pair up in ordinary superconductors, but governed by a different fundamental force. A state with internal structures and symmetries unlike anything we can study in the laboratory. A state that may be common in the deepest parts of dense stellar remnants and entirely absent from the rest of the visible universe. What is in the core of a neutron star may be something that exists nowhere else. Not in the sun, not in any planet, not in any cloud of interstellar gas, not in any galaxy in any direction. The deepest interiors of neutron stars may be the only places, anywhere in the cosmos, where these phases of matter can exist. And every neutron star may contain a small kernel of substance that the rest of the universe has never seen and never will see, except indirectly through its gravitational signature, through the way it shapes the star above it. Somewhere in one of those layers you are now. The atoms that used to be your skin have been dissolved into the crystalline iron of the crust. The neutrons that used to be inside the protons, that used to be inside the nuclei, that used to build your bones, have been added to the great superfluid ocean of the interior. The carbon that used to form the lipids in your brain has been split apart by pressure, its protons and neutrons separated, its electrons absorbed by other protons in distant parts of the star, its quarks, possibly even now, drifting in some quark soup at the center of a structure that contains the mass of a sun. You are part of the star. You are part of the star. You are the star. Read that, slowly. Let it settle. Because it is the truest sentence I can write about what has happened to you. The body that began this fall is gone, but the matter that composed it is not gone. The matter that composed it has been redistributed. The matter that composed it has joined a much larger thing. The atoms in your fingernails are now in a different state of matter than fingernails have ever been allowed to occupy. The water in your eyes is now part of a superfluid ocean that flows without friction. The iron in your blood, ancestral, ancient, forged in the death of some other star long before your sun was born, has come home. It has returned to a place very like the place where it was made. The journey that took it from one stellar interior to another has lasted billions of years. Now it has come back inside the matter that gives stars their final form. You have not died in the way you imagined dying. You imagined death, perhaps, as an ending, as a closure, as the moment at which a person ceases to be. Death, as you understood it before tonight, has a shape. The shape is small. The shape is local. The shape is contained. This is not that. What has happened to you is larger than ending. What has happened to you is incorporation. You have not been extinguished. You have been added. You have been taken up. The boundary that defined you, the small, soft envelope of skin that separated your atoms from the rest of the universe, has dissolved, and the atoms inside that envelope have rejoined the cosmos in a more direct way than any living thing usually rejoins it. The dust to dust of every old eulogy has been completed, but completed inside a star, inside the most extreme structure that matter is permitted to take, inside a thing that will continue to exist for spans of time, so long that the words to describe them mean almost nothing. The sun will die. In something like 5 billion years, the sun will exhaust its hydrogen, swell into a red giant, swallow the inner planets, and eventually shed its outer layers to become a small white dwarf, which will slowly cool over trillions of years. The sun will be gone, in any meaningful sense, long before the neutron star you have joined will have changed in any noticeable way. Neutron stars cool, they slow, they evolve, but they do so on timescales so vast that the death of an ordinary star is, by comparison, the flash of a single eyelash. You have outlasted the sun. You have outlasted the planet on which you were born. You have outlasted the star around which that planet orbits, by some staggering multiple, by some span of time that does not fit inside any human accounting. You have not ended. Something stranger has happened. You have become a place in the universe where the laws of physics behave differently. You have become part of an object that bends light. You have become part of a structure that rings without anyone to hear it. You have become, in some literal and unsentimental way, a tiny contribution to the singing of a star that began before any of your ancestors stood upright and will continue long after any creature that resembles you has gone extinct. The story is not finished. There is still a small piece of it left. There is still a return. There is still a meaning to gather. There is still the question of what any of this is for, and what it asks of you, and what it gives back to you in exchange for the body it has taken. That is the next part. That is the closing, and it is, in some ways, the gentlest part of the journey. Take a slow breath now, a real one, not a thought of a breath, an actual breath, drawn into actual lungs, in the room where you actually are. Feel it move into your chest. Feel it leave again. Feel the small shift in the weight of your body as your ribs rise and fall. You did not fall. Your body did not leave the bed. Your body did not cross interstellar space. Your body was not torn into a column of streaming atoms. Your body was not added to the crystalline iron lattice of a collapsed star and dissolved into a superfluid sea of neutrons, and possibly contributed, in some small theoretical way, to a core of quark matter that exists nowhere else in the visible universe. None of that happened to your body. Your body is here. Your body is whole. Your body is breathing, slowly, in a room that is presumably quiet at this hour, on a planet that is presumably still turning beneath you. What you did was think. What you did was follow a chain of physical reasoning, step by step, all the way to its strangest possible end. What you did was take your mind on a journey that no instrument can take, that no spacecraft will ever take, that no living thing will ever survive long enough to actually experience. The fall was real in the sense that the physics describing it is real. The fall was real in the sense that if a body were to do what we just described, all of those things would happen to it in roughly the order we described them. The fall was not real in the sense that you did it. You did not do it. You only saw it. You only thought it. And there is a long tradition, going back at least to Einstein himself, of physicists doing exactly that, of carrying out experiments inside their heads that the universe would never permit them to perform with their hands. So you are still here. Your body never moved. But something else may have moved, slightly. The way you understand the matter you are made of. The way you understand the gravity that holds you to the bed beneath you. The way you understand what time is, and whose time is whose, and what it means for two clocks in different parts of the universe to disagree about the duration of the same event. Those things perhaps have shifted in some small way in the time we have been together tonight. And that is the whole purpose of what we just did. Not to take your body apart. To take some of your assumptions apart, and to leave you, on the other side, with a slightly larger sense of the place in which your body actually sits. Let me try to give you something back, in exchange for what we put your imagined body through. You are made of these objects. I do not mean that as a metaphor. I mean it as a statement of physical inventory. The atoms inside your body, the heavy ones, the ones beyond hydrogen and helium and the lightest few elements, those atoms were not made on Earth. They were not made by the sun. They were made elsewhere, in events very much like the one we just described. in environments that no chemistry on a quiet planet could ever reproduce. Most of the heavier metals, the silver, the gold, the platinum, the iodine in the thyroid gland at the base of your neck, the strontium, the rare earths, were forged in the collisions of neutron stars. They were made when two of these objects, both of them long-dead remnants of much earlier stars, spiraled toward each other across billions of years of slow orbital decay, met in a single instant of unimaginable violence, and threw their crushed matter outward into the surrounding galaxy in clouds that took a long time to cool and a longer time to gather and an even longer time, eventually to coalesce into planets and into living things and into the bodies of those living things. The iron in your blood may have a different origin. Some of it came from ordinary supernovae, the explosive deaths of massive stars, the same events that produce neutron stars in the first place. Some of it came from neutron-star collisions. The exact mix is still being studied. What is not in question is that the iron in your blood is older than the planet under your feet. It existed before there was an Earth. It existed before there was a sun. It drifted as part of a vast, diffuse cloud of stardust through some forgotten region of the galaxy for millions of years, before that cloud gathered itself together under gravity and began to form the solar system you happen to live in. And then it sat, patiently, in the rocks and the seas and the soils of a young Earth, for billions more years, until biology found a use for it, until it was incorporated into the hemoglobin of a small invertebrate, until it was passed up the long ladder of evolution, body to body, organism to organism, eventually arriving in you. So when we said you were made of the echoes of neutron stars, we did not mean it poetically, we meant it materially. The objects we have spent this story falling toward are the objects that built you. The matter that composes your body is, in some real sense, debris. Debris from violent events long before your existence. Debris that has been recycled over and over into the structures of stars and planets and creatures, before settling, for now, into the temporary form that you happen to call yourself. You are not separate from these objects. You never were. You are a small, slow, lingering presence inside a much larger story, and the story includes them, and the story includes you, and the story does not draw any line between you and them that the universe itself recognizes. In August of 2017, humanity heard one of these objects meet another for the first time. Not heard with ears, heard with instruments, with detectors, with long arms of laser interferometry stretched across stretches of Louisiana and Washington State and Italy. The detectors are called LIGO and Virgo. They are designed to feel the smallest tremors in the fabric of space itself. They are sensitive to motions 1,000 times smaller than the diameter of a proton. They have been refined by generations of physicists and engineers into the most precise rulers ever built by human hands. On the morning of August 17th, 2017, those rulers picked up a signal. It was not loud. It was not dramatic. To an untrained eye looking at the data, it was a small rippling curve, lasting about 100 seconds, climbing slowly in frequency from a low rumble to a higher whine before fading out. But the shape of the signal was unmistakable. It was the shape predicted by general relativity for the merger of two compact objects spiraling into one another. The masses, when the physicists worked them out, turned out to be too small to be black holes. They were neutron stars, two of them, in some other galaxy, 130 million light-years from Earth. Two collapsed cores of long-dead stars had completed an inward dance that had begun, in all likelihood, hundreds of millions of years earlier, and they had met. And the meeting had sent gravitational waves outward in every direction at the speed of light. And 130 million years later, those waves had reached our planet, and our instruments had felt them. Within seconds, NASA's Fermi Gamma Ray telescope, looking outward into the sky for an entirely different reason, registered a short burst of gamma rays from the same patch of sky. The two events were linked. Within hours, observatories on every continent had pointed their telescopes at the location indicated by the data. By that evening, they had a visual, a new point of light in a distant galaxy. A new event in the sky, a neutron star merger, caught in the act, witnessed simultaneously through the bending of space-time and through the light it produced. It was the first time in human history that any cosmic event had been observed in both gravitational waves and ordinary light. The astronomers gave the event a name, GW 170817. The letters and numbers stand for gravitational wave, and the date, August 17th, 2017. The event itself, in the language the universe speaks, has no name. The event itself happened 130 million years before any human being could have given anything a name. By the time the news of it reached our telescopes, the entire history of human civilization had unfolded, and the long ages before us had unfolded, and the early branches of the mammal family tree had unfolded, all on the slow march of time between the moment the two stars touched and the moment we noticed. What the merger produced, in those last seconds before the two neutron stars became one, was a fireball of crushed matter expanding outward. The fireball was unimaginably hot. The conditions inside it allowed nuclear reactions that could not have happened in any other environment. Heavy elements were forged: gold, platinum, uranium, iodine. The slow rare metals were made in their billions of tons in a single moment of impact, and then flung outward into the surrounding galaxy in a cloud that astronomers on Earth watched glow and fade across the following weeks. You are watching this video on a screen that probably contains traces of those same elements. You are wearing, perhaps, a ring of gold or a watch with gold contacts inside it. You have iodine in your throat, made in events like this one, made nowhere else. You are not metaphorically related to neutron star collisions. You are physically a small downstream consequence of them. So when we said, earlier, that you have always been a part of the star, we said something true. You have always been a part of the star. You are now, even at this minute, even in the silent room where you are listening to this voice, made of the products of stars like the one we fell into tonight. Your body is the slow, long form of their afterlife. Your body is what their matter does after enough time has passed. Let me bring you back to your body now. Wherever you are sitting or lying or curled in some configuration that your body has chosen for comfort. There is weight in that body. There is the slow rhythm of your breathing. There is the dim background of small sensations, the temperature of the air on your skin, the texture of fabric, the small soft sound of whatever is around you. Outside the room, perhaps, there is a night. Perhaps the night is quiet. Perhaps the night has the small distant noises of a city, or the soft rustle of trees, or the simple silence of a country place. Perhaps you cannot hear anything at all because your headphones are filling your ears with this voice. Whatever the conditions, you are there. You are still there. You are still you. Feel the weight of yourself. Feel where your body presses against whatever is holding it. The mattress, the cushion, the floor, the chair. There is a downward pressure, gentle and constant, that has been holding you against the surfaces of the world for every moment of your life. You barely notice it. You have not consciously thought about it in years, probably. It is the most familiar sensation any human being has ever experienced. It is so familiar that we have, almost entirely, stopped feeling it. That pressure is gravity. The same force we have been talking about for the past several hours. The same force that crushes a sun into a city. The same force that bends light around a sphere of polished iron. The same force that makes the inside of a neutron star a place where matter behaves in ways that have no counterpart anywhere else. That force in the form it takes on the surface of the Earth, is what is currently holding you gently to your bed. 200 billion times weaker here than it is down there. 200 billion times less, and yet enough. Enough to keep you, enough to hold you in place, enough to allow the slow rituals of falling asleep, of dreaming, of waking, of moving through one more day, of being alive on a small, wet planet in an unremarkable corner of an ordinary galaxy. The iron in the small staining on your pillow, the dried trace of a nosebleed from last winter perhaps, or the fainter rust of skin oils that has accumulated over many nights of sleep, is older than that planet. The iron in the soft inside of your wrist, the iron that gives your blood its red color, the iron that has carried oxygen through your body for every minute of your existence, was forged before the Earth was a coherent thing. It was already old when the solar system first began to form. It is, in any honest accounting, a guest in your body, a long-traveling guest. A guest that will continue traveling after your body has finished with it, for billions of years more. You do not own that iron. You are borrowing it. The neutron star you fell into tonight has borrowed iron of its own, from earlier stars, from earlier events, from a chain of cosmic recycling that began nearly 14 billion years ago and shows no signs of stopping. The iron is older than any of us. The iron will outlast any of us. We are small temporary arrangements of much older matter, and the matter does not particularly notice that we exist. And the matter will continue to exist in some form long after we have ceased to be the arrangements we currently are. That could sound bleak, if you let it. But it is not bleak. Or, it does not have to be. It can be, instead, a kind of strange, quiet companionship. You are made of things that have been around for a very long time. You are not alone in your body. You are accompanied by ancient travelers. The atoms that compose you have been, in some sense, witnesses to the deaths of stars, to the slow gathering of solar systems, to the long patient unfolding of the universe. And now they are here, for a short stay, doing the small, soft work of letting you breathe and letting you think and letting you wonder, briefly, what it might be like to fall into the kind of object that some of them once helped to make. Now, close your eyes, if they are not already closed, or keep them open. Either is fine. Feel the bed beneath you again. Feel the gentle, persistent, almost imperceptible pull of the planet drawing you downward. The same physics that built the star we fell into tonight is the physics that built your house, your bed, your body, the air you are breathing. There is no different kind of physics for the cosmic and the small. There is one set of laws, and those laws apply equally to the most extreme object in the visible universe, and to the quietest moment of a person preparing for sleep. The star is still out there, somewhere. Many of them are. They are spinning, slowly slowing, ringing in frequencies no ear could ever hear, holding their secret interiors against pressures we will never be able to recreate. They will be there long after this night. They will be there long after this voice. They will be there long after every memory you currently hold has dissolved back into the substrate of matter from which it was briefly assembled. You will not be there to see them, not directly, not in person, but some of you already is, some of you has always already been. The carbon in your fingertips, the calcium in your jaw, the iron in the small inside of your eyelid. They are old, they are widely traveled. They will continue after the small experience of being you to be something else. They will keep going. So rest now, or let your mind drift now, or simply let yourself sit with the strangeness of what you have just imagined. There is nothing to resolve. There is no neat conclusion to put on top of what we have just done together. The universe does not particularly offer those. The universe offers instead this, a bed, a breath, a body, a slow, gentle weight. And far away, in directions you will probably never look in, the silent crystalline song of stars that you are, in some small literal way, already part of. Sleep well, if sleep is what you are heading toward, or stay awake gently with the thought. If waking is where you find yourself, either is honest, either is enough. The neutron star is still spinning. You are still here, and the night, for now, is yours.